In this video, we'll look at a surprising result that states that under certain conditions, a linear autoencoder is actually as powerful as a nonlinear autoencoder. So an autoencoder, as we've said before, is part of a neural network that first encodes the input into a hidden layer and then decodes it to obtain a reconstruction we call X hat. And in the previous videos, then I was suggesting we'd use in the encoder in nonlinearity applied on the linear transformation of the input. For feed-forward neural network for classification, we also justify using a nonlinearity because it would yield a nonlinear classifier which would be more powerful than a linear classifier. So now let's consider the question, for autoencoders, do we actually gain something by having a nonlinearity? Or would removing it, so not having this or this here, and just having a linear transformation for the encoder, would how powerful would that be? How good would this autoencoder be at reconstructing its input if we trained it on some data? So what we'll actually show is a pretty surprising result. It turns out that the linear autoencoder is actually optimal under certain conditions. That is, it will give you a reconstruction error that for a given number of hidden units is as small as it can be. And this result applies if we consider the square difference error. And it applies if we assume that the decoder is linear. So for the squared difference error or the square difference loss, I suggested we use a linear decoder. So in that case, we can actually show that a linear autoencoder will be optimal. It will give you the best training error it can for a given number of hidden units. So we'll show a sketch of that actual proof. And for that, we'll need this particular result here, which I'm describing. So if we have any matrix A, and which we can write into its singular value decomposition, so that is, we can write A as the product of a U and a U matrix, which has its columns, which is orthonormal, so its columns are orthonormal vectors. Sigma, which is a diagonal matrix, and on the diagonal of the matrix you have the singular values of the matrix, and then V transpose would be another orthonormal matrix. So this is what is being stated here. So imagine this matrix A, and imagine that we write its single value decomposition like this here. And now consider the particular case where we'd be selecting only the k largest singular value. So imagine on the diagonal of the sigma matrix, we'd actually had ordered the singular values in decreasing order. So the first one on the top left of the matrix would be the largest singular value, and then it decreases as we go along the diagonal. And so imagine then that we just select this submatrix by selecting the k first rows and columns, and then we'd select the left and right orthonormal vectors in U and V. So that's what I'm noting here. Then we can actually show that, imagine for this matrix A, we wanted to find another matrix B, which is of rank K. So it's and K would be presumably smaller than the rank of A. So imagine we want to find this sort of approximation B of A, and it's an approximation that's less complicated in the sense that it's a matrix with a lower rank. And we want to find the approximation that minimizes the Frobenius norm between A and B, sort of the difference between A and B. That makes so the approximation B that is closest to A, according to the Frobenius norm. So that's what is stated here. Argmin, so the matrix B, with the constraint that B needs to be a rank K of this expression here. Well, it turns out that the solution to that optimization problem, so the matrix B star that optimizes the Frobenius norm here, is actually just a matrix whose singular value decomposition is made of the matrix B star that can be written as the product of the the selected first k columns of U, the submatrix that selects the k first rows and columns of sigma, and then V transpose, where V, we've also selected the k first orthonormal vectors, k first columns. So in other words, by arranging the matrix like this, then it's actually easy to get an approximation of it that is as best as possible for some given ranks. We just select the part of that expression that corresponds to the k largest singular values. Okay, so this is a theorem that we won't show this theorem, but we'll use it to show the proof that a linear autoencoder is optimal. Okay, so now let's do the proof of optimality of the linear autoencoder. It's really just a sketch because I'm going to be making some assumptions. One assumption that I'm going to make is that the number of training examples, the number of these xt's here, is going to be the same as the number of dimensions in the input x. So essentially this sum here is over the same number of elements than this sum here. So when we're training an autoencoder, that's what we want to do here. We want to find the parameters such that we minimize the average or the sum, that's equivalent, of the reconstruction error, so the squared difference. And let's assume that this here was computed by a linear encoder. So we want to be able to analyze that case. So another way of writing this expression would be as follows. So we want to minimize this expression instead. So this whole expression here, we can write it as half times the Frobenius norm squared of this difference. So in particular, in this expression, capital X here is going to be the matrix, where the columns of that matrix are the different training examples. And so in other words, because I'm assuming we have the same number of training examples as we have dimensionalities, the size of the, so the name number of training examples as the size of these vectors, then this matrix X is going to be squared. And that's just going to facilitate the proof. We can generalize the proof to the general case, but I'll just, for simplicity, consider that specific case. So that's what X here is going to be. And then H of X, I'll call that the matrix whose columns are going to be the encoder outputs for each training example xt. And then if we multiply by the decoder weights W star, then by doing this, then we would obtain our reconstruction, because W star, the first column of that expression here, that would be the result of multiplying W star by the first column of H of X. And so all the columns of those matrix of that matrix would be all the reconstructed vectors. And then if we take the square of the Frobenius norm, we do get the a double sum, so a nested sum over the squared of the reconstruction of each element in the input training examples and their reconstruction. Now notice here that we have a greater or equal. We don't have an equal. And that's because I'm also going to assume that H of X here is actually any matrix, whatsoever of size number of hidden units by number of training examples. So we're not actually yet going to constrain it to be the result of a linear encoder. We'll just assume it's any matrix. And then after that, we'll actually show that if we minimize this, that the greater or equal is actually an equal, if we assume that this was the result of a linear encoder. But for now, let's just look at this particular problem where H of X can be any matrix. Okay, so now what's the result of that minimization here, which is here? Well, from the theorem we just saw before, then if we take X and we consider its singular value decomposition like this, and well, we notice that this here is actually a low rank matrix, and the rank of that matrix is going to be at most the number of hidden units. So if we think of K as being the hidden layer size, the number of hidden units in the encoder, then the previous theorem tells us that a solution for this would be to have W star be equal to, say, the part of the U matrix that considers only the first K columns times the sub matrix in sigma that considers only the first K rows and columns, and then H of X could be this. It could be the rest of the expression. So it could be V transpose, where V we've taken the K first columns. We could have put sigma here as well. That's another solution. But let's just, this is a valid solution, and it does minimize that expression based on the previous theorem. All right. Now, let's see whether this particular H of X, which takes that form and minimizes this, can actually be expressed as a linear encoder. And then if we do that, we finished our proof. So H of X is equal to that. That's exactly what we have here. And now I'll just essentially multiply by the identity, where because this times that is the identity. So this matrix times its inverse here, that's just the identity. So I'm not changing anything in the equation. And now I'm going to replace X here by its singular value decomposition. So X transpose is going to be the transpose of that expression if we put it in the singular value decomposition form. So that's V times sigma transpose times U transpose times U times sigma times V transpose. So that's comes from this, and this, this is that here, and this is here, this whole thing here, and this whole thing here. And then similarly for that matrix and that matrix, which actually I'm just going to take the singular value decomposition of that matrix, which we find here. Now, then we notice that this times that, that's just the identity matrix because U is orthonormal. So we just get this expression. These two cancel out. And then I'm going to write this inversion here as that. So indeed, we notice that if I take this and I multiply it by what's within the inversion, so this times that, that's just the identity matrix because this cancels out with that. This matrix times the inverse of that same matrix, that's going to be the identity. And then V times V transpose, that's also going to be the identity. Okay, so I've just rewrote this part into that form instead. Next, we notice that this times that, that's also the identity because again V is orthonormal. So we don't see it here anymore. We apply the same thing here, but now because this is the transpose of only the K first columns of V, then we get the identity matrix, but where we've selected only the K first rows of that identity matrix. Okay, so this will be a matrix of size K times dimensionality of the input space. And it's going to have ones on the diagonal and 0 elsewhere. So that's this matrix here. Next, I'll just apply the inversion and notice that if I inverse the product of a matrix, then it's the product of the inverses, but the order has been inverted. Okay, so that's why this is equal to that matrix inverted times that matrix inverted. Now I notice that this matrix times its inverse, that will be the identity, so they cancel out. So I get this expression. And then now I have this, the result of that matrix times that matrix. I'm multiplying on the left by this identity matrix, which for which we consider only the first k rows. So what this matrix is going to do here, this matrix here, is that whatever is happening here, it's only going to select the first k rows of the result of that expression, and in particular the entries in that matrix. And so the k first rows of that matrix can really be computed only by considering the sub matrix of sigma inverse that corresponds to the first k rows in the first k columns, and multiplied by the U matrix transpose, but where we've taken only the k first columns of that U matrix. So if you think about it a little bit, doing that is equivalent to this, because this selects only the k first rows of that matrix, and these rows can be obtained just by multiplying these two submatrices and submatrices of this and that. And then we notice that we have an encoder that was computed by taking all the inputs and then linearly transforming them, because this is just a linear matrix. So this could be our matrix W in an encoder. So h of x can be expressed as a linear encoder. H of x is also, which has this form, is also the optimal solution for minimizing this. So if we want to optimize that with the if we want to optimize this thing here, then the best we could do would be this, and this could be obtained by having this be a linear encoder. So the best reconstruction we could ever get if we have a linear decoder is to have this matrix here being equal to that, and this expression here can be obtained by a linear encoder. So thus we've showed that the best autoencoder here with a linear decoder is achievable by a linear encoder. All right, so so this is just what I've said. In h of x, we should take x and multiply it by that matrix, so that could be w. And then w star, it could be the other part of the expression in the SVD theorem that we use for the low rank approximation. And with these two expressions, then we've reached the best we can in terms of reconstruction error. That's what we've just shown. It's the best in terms of the square difference error or square difference loss. It's also the best if we have a linear decoder. Those were the two assumptions we were making while we were making that proof. And also it's the best, so optimality here means the lowest training reconstruction error. It doesn't necessarily say something about generalization error. But if we have more and more training data, then eventually training error converges to generalization error. So still that's it would mean that for a large amount of training data, we can expect that this linear autoencoder will actually do really well in terms of reconstruction error. So that's kind of a surprising result, and that perhaps suggests that there's something sort of broken about the autoencoder formulation that we've presented so far if we want to consider nonlinear features, nonlinear encoders. And finally, to finish up, I'll just mention that if we normalize the inputs such that we take each input and then we subtract the average of all training inputs, and then if we also divide by this factor here, then we can actually show that the encoder corresponds to principal component analysis. And so indeed, if we're using this, then the singular values and the left vectors are actually associated with the eigenvalues and the vectors of the covariance matrix of the training examples by doing that transformation. I won't make the demonstration. You can try it out. It's not too complicated. But so in other words, there's a relationship between autoencoders and principal component analysis, and with that pre-processing, principal component analysis is really optimal in terms of encoding data into a hidden layer size of size k, and in such a way that we get a really good reconstruction error. All right, so that's it about this surprising result about linear autoencoders.